Hello everyone. In this practicum, we designed a closed-loop temperature control system using PID controller in MATLAB Simulink. To better view how the system behaves and performs, we gave the five important aspects related to controller signal conversion, system turning, stimulation, accuracy, and real-world extensions. These concepts helps us to see how theoretical control systems are applied practically in engineering. And the first concept involves computing PPI and PID controllers. A proportional controller reacts quickly to error but cannot completely remove steady state error. So the final temperature may not exactly match the set point. A proportional integral controller improves this by adding an integral term that accumulates error over time and discard the steady state error. Although it may slightly increase or overshoot, a PID controller further enhances system performance by adding a derivative term that predicts future error changes, uh, thereby decreasing overshoot and improving stability. Hence, each controller has its own advantages depending on the system requirement. The second concept explains the role of the Simulink PS and PS Simulink converters. Since Simulink work with the mathematical signals and SimCape works with physical signals such as temperature, direct connections between them is not possible. The Simulink PS converter converts Simulink signal into physical signal, so they can be used in case blocks like a controller temperature source. Similarly, the PS Simulink converter converts physical signal from a temperature sensor back into similar signals for further processing and display. These converters ensure smooth communication between both domains. The and the third concept focuses on the derivation gain KD in the PID controller. The derivative term predicts the future trend of the error by seeing its rate of change. Increasing KD helps reduces overshoot and stabilizes the system by damping oscillations. However, it can also amplify noise and make the system unstable if not tuned properly. In this practicum, KD is set to 0 because the system already achieves stable performance using only proportional and integral control, making derivative action unnecessary. The fourth concept that deals with the solver configuration block, which controls how the Simulink is executed. Parameters like relative tolerance determine the accuracy of the simulation. A lower tolerance value results in more accurate result but increases computation time, while a higher value speed up the stimulation but reduces accuracy. Therefore, selecting appropriate solver settings is important to balance accuracy and efficiency in the simulation. And the fifth concept discuss about the expansion of expanding the system by adding thermal mass and disturbance input. Thermal mass represents the stability of a system to store heat, which slows down the heating and cooling process, making the system response more realistic. Disturbances such as external temperature changes test how well the controller can maintain stability under varying conditions. These acts make the model closer to real world industrial systems and improve understanding of controller performance. So, in conclusion, these five concepts provide a deeper understanding of how a temperature control system operates and how different parameters affect its performance. By seeing controller types, signal conversion, turning methods, stimulation settings, and system extensions, we gain practical knowledge of designing efficient and stable control system. The the understanding is essential for applying control theory in the real world engineering applications such as industrial automation and smart system. So if you found this video useful, kindly like, share and subscribe to my channel. Thank you.